Syzygy, episode 84, Spot Speeds Up. And welcome back for another edition of the Syzygy podcast. My name is Chris Stewart, and joining me fantastically on the other side of her office desk is Dr. Emily Brunsdon. Hi, Emily.
Hello, hello.
You've had a busy week.
Yeah.
It's been a busy week. Unexpectedly busy. I hear yesterday suddenly became really busy for you. What's going on?
Yeah, well, some more people decided that they fancied spending a lot of money to go not very far, but nonetheless into space.
Including Captain James T. Kirk himself, Bill Shatner.
Yes.
Was on a rocket going into space, and including a guy who did his PhD at the University of Sydney while I was there that, you know, I ran into a number of times.
You're such a name dropper.
I know. And suddenly he's going to space. So Chris, Dr. Crispy is his DJ name, if you happen to be tuning into this one. Well done for going into space. That must have been really exciting.
Fab.
But Emily, what's your role in all of this? How did you suddenly get busy yesterday when they were going to space on Blue Origin, you know, manned mission number 2?
Well, apparently, if you just take the prefix of astro, you can apply that to a lot of different fields that I am supposedly an expert in.
All right. So you've graduated, have you? You've gone from, hang on, there's something about the moon, let's get Emily, because she's Moon Girl, to this is space, right? Who do we know who does space? Emily, let's get Emily on. So who were you talking with yesterday?
Yeah, so I had a chat with Sky News for a little while during the launch, and obviously coming back down again as well. And even good old BBC Radio York gave me a bit of a ring and said, you know, do you want to go to space?
And what was your answer?
Of course.
Of course. If you're paying, if BBC Radio York is prepared to pay, then Emily's going to go to space. I think that'd be awesome. I'd come and cheer you on. Not sure that I want to go to space. Do I want to go to space?
You do want to go to space.
I think it'd be fun. I think it's much more comfortable now.
Oh, yeah. If a 90-year-old can do it.
Well, there is that. But then again, it's not just any 90-year-old. It's William Shatner. I mean, you know, he's the dude. Anyway, that's exciting. Well done, Emily, media superstar and go-to person on anything that involves above about 100 Ks as far as we can tell.
Yeah, that seems to be the line.
You're now the expert on everything up there. So that's great. Fantastic. Well done. And of course, you dropped in a plug for the podcast.
Oh, yes, of course. Yeah. I had the Syzygy postcard conveniently placed in the background, although I think it was cropped out of several of the pictures of me.
Well, hello to the probably millions of new listeners that we now have as a result of you covering William Shatner going to space. That's not what we're talking about today, though. That's a digression. Today we're going to be talking about something which, amazingly, we haven't really done before. We're going to be chatting about something which is in our kind of local backyard, right, of the solar system. And in the solar system, there are a bunch of really iconic things, right? If you think about how would you describe, or what picture would you find to describe the solar system? People might go for the rings of Saturn. That's a really iconic picture, right?
They might go it's a favourite of many people who
indeed
need to look at other planets a little bit harder sometimes.
Well, remind us what you like. You have a thing about this, don't you? You think that Saturn's a bit of a prima donna, and your favourite planet is Venus?
Mercury.
Oh, Mercury.
Mercury.
Rocky little hot Mercury. But yeah, it doesn't get a lot of love except from this particular side of the astro podcasting world. So Mercury, big shout out. But I don't know that many people would be going, oh, Mercury is the iconic planet in the solar system. Probably not.
No.
Maybe more should, but I'm guessing not many do. But then you've got, you know, the sort of rusty red rock of Mars, the red planet. You know, there's that. But one of the other really iconic ones is the biggest planet in the solar system. It's Jupiter, and in particular, one physical aspect of that planet. Its big spot. Its big red spot. Right. This is an iconic thing in the solar system, and we've yet to talk about it. So
it's
here we are.
Crazy. How did we get this far?
Episode 84. The reason that we're going to talk about it today is because stuff's happening, right? Things change over time, and apparently Jupiter's big red spot is not quite what it used to be. So, Emily, what's going on up there on Jupiter? Take us through this one.
Yeah, so obviously when we look at Jupiter, even through a relatively small telescope, in fact, if you're in the Northern Hemisphere at the moment, Jupiter's quite nice, particularly in the UK and the evening sky at the moment. Easy target for a little telescope.
Mm-hmm.
Saw it actually just a few nights ago when we were out of the Astro Campus. So
very nice.
Great target. And if you've got a small telescope, if you get it really nicely focused, you can actually even see this feature on Jupiter.
Seriously?
So you can see the spot, yeah.
Wow. Like when you say small telescope, like how small is small?
I can't predict exactly what the small limit is, but we can definitely see it with our 16-inch and I think with our 12-inch as well.
Yeah, okay. So those are modest telescopes. It's not a pair of binoculars.
No.
With binoculars, you could see the moons, I'm guessing, maybe?
Yes, you can. Yeah, you can. So, yeah, but I'm not talking about you have to go to kind of like the biggest research telescopes in the world to see this stuff.
No. You can actually... So, wow, that's really cool. Okay. Because I've looked at Jupiter through small telescopes and binoculars and things, and I've seen the moons, which is cool enough. Like being able to say, oh, wow, those little dots, those are moons actually going around another planet. That's awesome. But haven't seen... the spot. So the fact that you could go and grab a modest-sized telescope and do that is really, really cool. Okay. Yeah. So hence it being such an iconic thing in the solar system. So what's going on with the spot? Why are we paying attention to that today?
Well, we've got some really exciting new research which has just come out from Michael Wong from UC Berkeley.
I think Berkeley? I don't know.
In California.
If you're listening to this in California and you want to write in and tell us how we're supposed to pronounce that, please do. That'd be fun. Let's go with Berkeley, I think. Yeah.
Let's do that one. Yeah. And what they've discovered is that actually, instead of kind of being a spot that's swirling around at a constant speed, the outer edges of the spot are speeding up.
Okay. I don't know if that's good or not. So let's delve into this. Is that a good thing? Can you even put good and bad on a large spot on another planet? Why don't we wind this back a little bit? Emily, what is it? What is this? Like it's big, right? When we talk about the big red spot, it's big on like grand scale. So what is this thing? How big is it? What are we looking at when we see that?
Yeah, well, that's a very good question. And we don't have all the answers, but we can at least describe what the spot is to our best observations. So Jupiter has an atmosphere, extended atmosphere. It doesn't appear to have a particularly solid surface underneath it. So it's not like kind of the Earth or Venus where you've got a rocky surface and then a thin atmosphere. It's just basically all atmosphere.
Right. Okay. So when we talk about it being a gas giant, it's gas all the way down?
Most of the way down. There's probably something interesting going on in the core, especially under the intense pressure from the outer layers. Because remember how Jupiter's huge.
It's big. Yeah.
So the gravitational force coming down into the center is huge. And we think there's some kind of metallic kind of core that's to do with its magnetic field and all this exciting stuff. But the important thing about its atmosphere is that of course means that it's a fluid and it moves. And even before you get to the point with a telescope of being able to see the spot, you can actually see the stripes on Jupiter from the different horizontal bands of clouds that happen. So you've got the equator and then you've kind of got parallel bands of clouds that go around Jupiter that way.
Some amazing pictures. Which mission was it that gave us some of the extraordinary images that have come out? I kind of feel like in the last decade or less.
So you might be thinking about Juno?
Yeah, probably.
Yeah.
When was that?
So 2017 or thereabouts.
I thought it was fairly recently. And then, a whole bunch of just amazing images were sort of dumped, freely available, I think, on the internet for people to go and just play with. And some people have sort of, played with and filtered and tidied those up into just some of the most extraordinary images.
They look like Renaissance paintings, don't they?
Yeah, they're just beautiful things.
Gorgeous.
Beautiful things.
Yeah.
Amongst which are, all these incredible bands of clouds. So these are what sort of layers, or not strata, because that implies sort of vertically, up and down away from the core. But bands going around in what sort of around as the planet spins. That's the idea?
Yeah, well, they're linked to the rotation, but of course, because it's a fluid, not the whole surface of Jupiter doesn't go around as if it's a solid ball. It's got what we call differential rotation. So some bands of clouds go around faster than others.
Okay. And so different layers are sort of mixing around at the boundaries and giving us these amazing swirly patterns and so on. Is there a fairly obvious rule to that? Like, is it sort of faster towards the equator and slower further away, or is it much more complicated than that?
I think the faster bands tend to be towards the equator, but I don't think it's kind of like a direct relationship that the faster you are, the closer you are. There seems to be some really interesting angular momentum sort of features going on there that I haven't looked into in incredible detail, but yeah, some of the bands go faster.
But come on, Emily, you're an expert on everything above 100 kilometers. Surely you know all about this stuff. So can I just back up a little bit? It just suddenly occurred to me, I don't actually know what it is. Like, what is Jupiter made of? What are these, like, what is the atmosphere do? What are we looking at with all of these amazing bands and colors?
Well, the interesting thing is that Jupiter is mostly just leftover sun.
Okay. So it's stuff that the sun formed out of, but it wasn't quite big enough to form its own star. Considerably smaller than it needed to be, I guess.
Yeah, so we have sort of two different types of atmosphere in the solar system. We have primary atmospheres and secondary atmospheres. So primary atmospheres were just the stuff that was left over when the sun formed. It didn't quite make it into the sun. Lots of gas, mostly hydrogen, of course, but then a little bit of whatever else was left over in the cloud of gas and dust that formed the sun. And then they've held on to that atmosphere. It's primary. It's the first atmosphere that they've had.
Right. And Jupiter's one of those.
That applies from Jupiter out.
Okay. Yeah.
And however, planets like Earth, Venus, even Mars have had secondary atmospheres because the sun's sort of light and powerful solar winds have actually stripped off the primary atmospheres, and then it required other chemical elements, usually heavier chemical elements, to come in and form to make these secondary ones later on from tectonic activity, outgassing, that kind of thing.
Right. And we've talked a little bit about the difference between the inner planets and the outer planets before. So when you say Jupiter is sort of that primary atmosphere, so does that mean that what we're looking at when we look at Jupiter, is that mainly hydrogen then?
Mainly, but actually all the interesting stuff is, of course, the stuff that isn't hydrogen.
Right, okay.
So there's lots of kind of complex molecules and things going on. You've got lots of ammonias, lots of methane, etc. And then even some quite exotic sort of particles. We don't really know, for example, why exactly are there different colours in the different bands of clouds.
Like, I would have thought that would be one of the first things you'd nail down. Not that I'm blaming you. I'm not saying anyone's done anything wrong. I'm just saying you look at the thing and it's such an extraordinary thing to look at. And the patterns and the colors are so amazing. Just naively, I would have thought, well, surely you'd have nailed that one down. Like,
yeah, it seems even the Great Red Spot, we don't know exactly why it's red, for example.
Weird.
Yeah,
so
we've got some reasonable ideas that are probably along the right lines. So we think that there's some different chemical elements that are being sort of dredged up or at least exposed to the ultraviolet light because remember, we're only looking at the very tops of the clouds here. So they're being exposed to that light, which is changing their chemical composition and changing them into sort of basically redder things. But the exact process is not known.
Is the problem here that I mean, it sounds really quite complex because you've got a lot of stuff mixing around, and, fluid dynamics is hard enough as it is. Atmospheric chemistry is hard enough when you can actually go out and take a sample of it. Trying to do that on another planet is even harder. Is part of the problem that we can't actually go and take a sample of it? Like, we can't actually get there to get in really close and stick a jar out the window and grab some and have a look at it?
Well, yeah, absolutely. And particularly when you're talking about sort of quite significant changes over a relatively small area in terms of if we turn our telescopes to look at Jupiter, then we can take an overall kind of spectrogram of what are the chemical species that we can see. But it's very hard to say, is that coming from that cloud or is that cloud or is that spot?
Yeah, I hadn't really thought about that it's not that precise. You can look at Jupiter and go, it's got this in it. But but is that there or is it over here? And so you're saying you can't look at a particular bit like, the boundary of the spot or something like that and say, what's in there with that method? Because it's just not that precise.
And we're not getting as much signal because this is all reflected light as well from the sun. So it's all very tricky.
Isn't that weird? I kind of take for granted, particularly after this many episodes of this podcast, Emily, you've done such a good job of selling me how good astronomy is at, we can look at that and figure out what it is, that I just blunder into things like this and think, well, surely we know all about the surface of Jupiter and what it's made of and how it's put together and why this does that. And actually, every once in a while you realise, no, it's much harder than that. It's a lot more subtle and complex than that.
It's often true in astronomy that we know more about very, very distant objects in the universe than we know about things in our backyard.
Which is weird, right? But that's kind of nice. It leaves us stuff to do. So, okay. I had one other question which I wanted to ask, which was, there's a lot of hydrogen and then there's all this other stuff there in the clouds, in the atmosphere of Jupiter. Is all of that stuff left over from when it was formed? Like, did the solar system form out of stuff that was already that mixed and complex? Or has Jupiter gained a lot of extra complexity over time?
That's a good question.
Thank you. I thought so.
Yeah, it is. So I guess the majority of what Jupiter is made of was from its formation, but certainly it has acquired new stuff along the way. We only have to look back, I guess, a couple of decades when we saw the comet Shoemaker-Levy hit Jupiter. And this is the kind of thing that Jupiter does all the time, right? There's lots of things that it's got a significant gravitational influence. So if you get in the wrong place and you're sort of a small body in the solar system, then, you might get eaten by Jupiter too.
You're going to get broken apart and sort of gobbled up by this massive planet. Yeah, that was amazing because it was... it's not just that we could say, hey, look at this comet, which is, it broke apart into like, a dozen pieces or something, and they all slammed into Jupiter. But they happened to do it from an angle that we could actually see really, really well. So there's some amazing sort of images of over a period of, I can't remember how long, but a fairly short period of time of these great chunks of comet slamming into Jupiter. And I mean, it didn't really do a lot to Jupiter, but it did enough that you could actually see, oh yeah, that bit there, that's where the comet bit hit, and it sort of swirled around in the clouds for a while, which is kind of cool.
Yeah, and you think that that's happened in our lifetime, then, over the course of the last 4.5 billion years.
Probably happened a lot.
Yeah.
Yeah, chances are. And so it will have picked up, all sorts of stuff flinging itself around in comets.
Yeah, lots of ices, water ices, complex organics even coming from the outer solar system. So, yeah, bits of pieces of stuff.
Cool. So, summary is Jupiter is a lot of hydrogen, a bunch of other stuff, and it's complicated, and it's got these amazing swirly patterns. But the one that we're focusing on today is the big swirly pattern known as the big red spot, the giant red spot, the great red spot. Does it have an official name?
It's the great red spot.
The great red spot. Okay. Yeah. So what is it?
Yeah, we should have probably led with that.
Well, let's bury the lead. We normally do. So what is this thing?
Right. I think, and kind of, I'm trying to channel my inner meteorologist here.
Okay.
It's a counterclockwise high pressure region, also known as an anticyclonic storm.
It's a storm, right? What you're describing here is a storm, and we get those, right? We have those here on Earth. It's a cyclone.
It's the largest storm in the solar system.
Well, okay, it's not just a cyclone. You could arguably say it's the cyclone, just as the James Webb Space Telescope is the space telescope. This is the cyclonic storm in the solar system. But for all of that, it's just a storm. Okay, so can we unpack that a little bit? There were a couple of different descriptors in there. Anti-clockwise?
Yep, anti-clockwise.
Counterclockwise, whichever way you want to say it.
Yep.
Not clockwise, the other one.
The other way.
Presumably that's because it's in a particular hemisphere, because that's what we get here on Earth, right? You get hurricanes or cyclones going one way in the north and the other way in the south.
Good point. Yeah, I hadn't thought about that.
So presumably that's the reason why it is on Jupiter as well?
Probably. I mean, you've got lots of centrifugal centrifugal forces.
Careful, we'll get emails.
No. The forces. What are the forces called?
Coriolis
forces.
Yeah.
Thank you. Knew it started with C.
Yeah.
There we go. It's not like these are relevant to my research at all.
No. Coriolis forces.
Yes, so you've got Coriolis forces going on. Yeah, so I imagine that, there's still questions about how angular momentum is distributed throughout the clouds of Jupiter and how it dissipates through these kind of storms. But one of the interesting, there's lots of cool facts about the giant great red spot that we're going to talk about. But one of them is it's lasted for an incredibly long time. At the upper estimate, we reckon it might be 356 years old.
356. Like, I was almost waiting for you to sort of 1,000, million, billion, wouldn't have been billion. So 356 is a long time, but not on astronomical scale.
Well, this is how long we've been observing it for.
Right. Okay. So it's at least that, and quite possibly much longer.
Yeah.
But at least that. And I guess that raises the interesting question of, like, how long would you expect something like this to last for? Well, like if we've been watching it for several hundred years, you might, and humans have been pretty good at that throughout our history. Well, if it's been there as long as I can see it, it must have been there forever, right? So clearly the spot is just a thing that Jupiter has and it'll be there forever. But that's not the case because it is changing, right?
It is changing. And what's interesting is that we thankfully do not have storms that last hundreds of years here on Earth, right? And the main reason for that is because the energy or the angular momentum is actually dissipated by friction through the rest of the atmosphere. So it basically runs out of steam.
Right.
Whereas in the atmosphere of Jupiter, that's not so much the case. There's not that way to dump the angular momentum to get it out of the storm, basically. So it's very, very likely that this storm will last for a long time yet. At least current predictions say it should last at least another 50 to 60 years based on very conservative models. But who knows? It could be thousands of years old. It could go for thousands of years in the future.
That's an amazing idea that like I really do have it's such a part of Jupiter, if you were to draw, like even any kid who's spent any time learning about the planets, if they were to draw planets, they'd probably draw Saturn with some rings around it. And they would probably draw a Jupiter with a spot on it, fairly high probability. And the idea that, future generations of children, not many down the track, would not do that because it's not there anymore. That's kind of weird. Yeah. We don't normally have in astronomical scales something that prominent being that time scale. Kind of feels to me like it's either over like that, or it lasts for effectively forever. I can't think of many other things which are sort of on the almost human time scale.
Yeah, it's interesting. I mean, even though your example about Saturn's rings, we just found out, was it a couple of years ago, that they're probably only, 10,000 years old, and the dinosaurs may not have seen them.
So had the dinosaurs been able to get their tiny little arms up to hold a telescope, they may not have seen the rings. Yeah, I hadn't really thought about that. But even then, 10,000 years is a long time. Whereas hundreds...
Yeah, well, I'm not saying that it really is 1,000 years. Maybe it will be another 10,000 years, the spot.
If the spot is still around in 100 years, I won't hold you personally responsible. Okay. So just going back to something you said a minute ago, storms on Earth don't tend to last terribly long. I mean, the biggest ones, things like, massive hurricanes, cyclones, last maybe days to sort of a week as they're building up over the oceans, hit land and just dump all of this energy and momentum on the land generally. Or maybe they'll head back out over the ocean and just slowly dissipate all that energy back over the ocean. But it's sort of a timescale of maybe a week, right? Smaller storms, hours to a day. It might be brewing up and then dump all of its energy. This one is considerably bigger, but is what you're also saying that there's just presumably less of a mechanism for it to actually lose that energy.
Yeah, exactly.
And transfer it somewhere else. And so it just keeps going, swirling around.
Yeah, exactly. Yeah.
Very cool.
Yeah, so it's very interesting. And if we think about the rotation of the spot, because I sort of like to sort of figure out, like, well, what does that mean, the spot's rotating? It's actually, again, it's not rotating like a solid body. So what's really cool is that the ring, that's the outer sort of boundary edge of the spot as you would draw it, that's the bit that's rotating quite quickly. So that's kind of going around once every 6 days or so.
Wow, that quick.
Yeah.
Because it's a big thing, right?
Yeah, absolutely.
Do you have any stats on it?
I've got you some stats on this.
Yeah. How big is this spot? Because it is big. That much I know.
It's that question does actually depend on when you measured it.
Right. Okay.
But we'll come back to that.
All right.
Currently, in around 2017, when the last sort of precision measurement was that I could pull out, was 16,000 kilometers wide.
Okay. Can we put that in some kind of context? What's the diameter of the Earth?
It's about 1.3 times the diameter of the Earth.
Wow. That's a really big storm.
Yeah.
Wow.
It's pretty big.
That's kind of nuts.
And that's on its longest edge. So if you imagine kind of it's an ellipsoid, it's although what's very interesting is the spot is, I guess you could call it shrinking or becoming more circular over time.
Okay.
So over the last, especially I think since the last 3 or 4 years, it's become much more circular. And there's some really interesting sort of pictures of you can get from going from almost like really long, not quite cigar, but, quite squashed circle coming up to being a much more circular shape in 2020, 2021.
Has it been sort of changing like regularly over time, or does it sort of squish and squash and get bigger and smaller? Or has it just been slowly running out of juice over those 300 years that we've known it's there?
Well, this is a really difficult question because the measurements that we have that are precision measurements are really only ever happened in the last couple of decades.
Right. Yeah, this is where it gets hard.
Yeah. And this is coming back also to the premise of, I guess, of the paper, because this paper is based on Hubble data, when Hubble's been observing this spot with really high resolution for about 11 years.
Okay. So 11 years, a lot of good data, but it doesn't really tell us terribly much about long-scale changes. And presumably, the vast majority of those 300 plus years that we've known it's there, it was very, very fuzzy. And, oh, look, there's a spot on Jupiter. And that's about as good as we could do.
Yeah, and even, well, I got read a bit about this because I got quite a little bit into it, because there's some really interesting sort of question marks about whether these observations from sort of 350 years ago are real observations or not. And there's some interesting characters that you might recognize along the way as well.
Okay, all right. Well, shall we delve back and do a little bit of history then?
History of the spot.
Let's do it.
So, of course, we've been observing Jupiter with the naked eye since people started looking up, let's be honest, right?
Sure.
But it wasn't until we had the application of the telescope, or the telescope applied to astronomy, that we started to see some of the more detailed things going on, which of course meant you're talking about the 1600s. So our first maybe record of Jupiter's Great Red Spot comes in 1665 from a name you might be familiar with, which is Giovanni Cassini.
Ah, yeah, okay.
Yeah. So Cassini was... as people were in those days, quite interesting characters, but someone who dabbled quite a lot in not only astronomy, but astrology. And
it was all mixed together. You know, Newton went in for alchemy. Like there was the boundaries between what we would now say is hard science, proper mathematical, no, this is the real thing, and slightly dodgy or very dodgy pseudoscience. We're quite sure as scientists where that boundary line is now. But it wasn't always that way.
No,
it wasn't always clear what was worthy of scientific pursuit and what was a dead end, because there's just nothing there. And astrology, look, people have been trying to predict the future through the stars for a really long time. Maybe, maybe not. Yeah, all sorts of possibilities there. Yeah. So Cassini was a bit of both.
Yeah. And you think about what people called themselves back in those days, right? They didn't call themselves scientists. They called themselves things like natural philosophers.
Yeah, which is just basically saying knowledge. I seek knowledge.
Stuff.
Well, yeah. Good. Using whatever tools you have available. So Cassini saw the...
Well, he wrote down that he saw a permanent spot, which is interesting because he used the word permanent, or whatever the Italian equivalent was. So he clearly looked several times over a period of time and decided that is actually a thing that is staying there.
Well, it sounds legit.
Yeah. He also noted the differential rotation of Jupiter, which... That's pretty cool.
Differential rotation, as in...
And then the clouds going at different rates.
Right. So was able to see that level of detail.
Yeah.
Wow. It wasn't just like I'm imagining being able to see through a very old telescope, a very blurry blob, which has a smaller blob on it. Right. And that's the spot. And clearly he's seen more than that.
Yeah.
Because he can see different bands going at different rates, which is impressive.
Yeah, so that was quite cool. Now, there is some discussion about this kind of area of science history as to whether or not there was actually a previous record of Jupiter's Great Red Spot in the previous year, in 1664. Mm-hmm. And this is something written down by another name you might also recall, which is Hooke.
Okay, Hooke as in because there have been a few Hookes, I think, haven't there? But there's Hooke as in Hooke's law.
This is the Hooke.
The Hooke, yeah. Hooke's all over a whole bunch of stuff in physics and astronomy as well, presumably.
Yeah, he did astronomy, he did mathematics, he did physics, he did springs, clearly.
Yeah, that Hooke.
So he does mention Hooke, but that he saw a sort of feature on Jupiter. However, the kind of consensus opinion is maybe that was actually another spot.
Oh, okay.
Because it was in the wrong hemisphere. Maybe.
Maybe he was looking at it upside down.
Maybe, yeah. It's all a bit like...
Maybe it was a smudge on his lens or something. Who knows?
Yeah. But, so maybe Hooke saw it first, but definitely Cassini.
We'll give Hooke half a point and Cassini a full point, and that seems fair to me.
Yeah, and then there was loads of observations made following that between 1665 and 1713. People got quite excited. And then they just stopped saying things about it, which is kind of weird.
That's weird, right? Because I can imagine the sort of astronomical gold rush when the telescopes get good enough and it catches on that, look, if you look at this thing, you can actually see detail. Like this thing that we've always thought of as just this little pinprick in the sky, very bright one. There's detail on it. Like we can see stuff. Quick, record that, do a drawing of it, write it down. I can imagine the gold rush that comes from that. Loads of people would then want to try to make discoveries. But it went quiet. Why?
Yeah, I don't know.
Weird.
The next mention we have of the Great Red Spot comes in 1831, 118 years later.
That's a big gap.
So either there was terrible weather for a really long time, people were not very interested, or there
might have been other stuff going on.
Records were lost if they were being made. It's just, or maybe the spot went away.
I guess that's possible, isn't it?
Yeah.
So it feels unlikely, but yeah, that's a really long time to not be saying anything about a really prominent feature on the biggest planet.
Yeah, it's really odd. Mystery. I like mysteries like that.
Cool. Okay, so that gets us into the 1830s, you say?
Yeah, and then fairly regular observations. What's interesting is that we do have some kind of good records, enough to say that at least from 1904 to 2004, so 100 years, the spot has shrunk to about half its size in the longest axis.
Wow, that's a lot.
It's a lot, isn't it? Yeah. I didn't realize this thing was so, like... not
changeable, variable.
I was going to say dramatic, but yeah, I guess it is. I guess it is dramatic.
Well, again, for something which I don't know, maybe I'm the only one, but something that feels to me like such an integral part of this big planet, for it to be so changeable over relatively short, human scale timeframes, is really surprising. And have we, like, it sounds from what you're saying, like what we've recorded is it getting smaller. Not that it, from this time to this time, it got much bigger and then suddenly it turned sideways. And that, no, it seems to be, everything you've said so far is it's getting smaller over time.
Yeah. I mean, in one axis at least. So it's not like it's not shrinking away to nothing because the other axis seems to be staying relatively stable. So what it's doing is going more from oval to circle.
Right.
And based on the past 100 years of change, if you just push that model forward, which is maybe not necessarily a good thing to do, but it's an interesting thing to do.
So sure.
Yeah, then it's going to be circular by about 2040.
Okay, and then what? Does it just, by the modelling, does it just stay circular? Does it go really, really thin? Does it...
Your guess is as good as mine. Cool. So it would be a really nice circle then.
Okay. Nice.
It's kind of satisfying.
Nice. A little bit sort of Death Star-ish, but okay.
So, yeah, the other thing that's very changeable about the spot, which I hadn't appreciated myself, is that the colour changes quite dramatically over time.
So the Great Red Spot, not always red?
Not always red. In fact, it varies in hue from kind of a, I guess, traditional English bricky kind of red to...
sort of a terracotta.
Yeah. Very nice. To white. Or pretty much just off-white, yeah. So there's times when actually the bands of clouds around Jupiter look red and the spot looks white. And then there's other times it's vice versa.
Weird. And is that, do we have any idea why? Like you said before, we don't really know what's going on down in there.
Chemicals in the atmosphere, maybe.
That's very hand-wavy.
Yeah.
It's about the chemicals. Well, yeah, it's an atmosphere. Ah, cool. Okay, so the Great Red Spot is not always as great and it's not always as red. So, okay, 2 for 2 there.
We might have to go for the little white spot in the future.
It's still a spot, though, so I guess we've got that. So we were sort of working our way through in history, and we got through into the sort of towards the present time. You said before that we had some really good observations from Hubble, but how have we been looking at Jupiter over, I don't know, the last several decades, the era of modern astronomy? We've obviously had a couple of missions to Jupiter. Have any of them had a really good look at this feature?
Yeah, absolutely. I mean, this is where, like you were saying, the images, say, from Juno, even since the Voyagers had Jupiter flybys, right, to look at.
Yeah, of course, and that would have been, what, in the
70s?
80s, 70s,
Well,
80s?
how long did it take to get there? Yeah, a little while. But yeah, okay. So, yeah, so as long as we've been sending stuff to the outer solar system, we always get it to fly by Jupiter if we can, because it's handy to get you that little bit slingshot.
Yeah. I mean, it gives you the speed boost, right?
Yeah.
And so you may as well take some good pictures while you're going past.
But what I love about this piece of research, coming back to, I guess, this particular paper that we're talking about, is that it's using Hubble data. Now, even in our last episode, we talked about, touched on the fact that even Hubble is not irrelevant now, right?
It's still going and it's still doing good stuff.
It's more than 30 years old, but even this last decade, which is the decade where these observations have been based on, it plays an incredible role in our understanding of our solar system because it's an instrument that has time, so you can point it at Jupiter fairly regularly, and it has been pointed at Jupiter fairly regularly to look at its surface features, and it's got the resolution to be able to measure those features. So I think the smallest feature that we can measure with Hubble on the surface of Jupiter is about 170 kilometers across.
That's pretty small. When you're talking about like a spot which is in the order of 1.5 Earths across, to be able to see features down to 100 or so kilometers, that's impressive.
It's very impressive.
From something here.
Yeah, yeah. Hubble's just around planet Earth. And so it does also, I guess, highlight again something we said last week, don't to hark on about it, but, James Webb is going to, again, be able to look at these planets in even more high resolution. So that's exciting.
And James Webb being, as we did discuss, almost exclusively in the infrared, is there stuff that we can learn about Jupiter looking down in the infrared? There must be all sorts of things.
Yeah, super useful. It's kind of like thermal imaging, right?
Right.
And even the spot has, it's slightly, I think it's cooler in the center than it is surrounding it. So there's a temperature difference. So you can measure that when you're looking in the infrared, which is quite cool.
Very cool. I like that. And just going back to Juno for a second, because that was, what did you say, 2017?
Around about, yeah.
So remind me, because that, even just in the name, Juno, like it's about Jupiter, that's what it's doing. What was Juno designed to do? Like it gave us a lot of beautiful images, but as we've discussed, beautiful images is not synonymous with astronomy. There's more to it than that. So what was Juno about?
So, was exploring Jupiter and its moons as well. So we have spoken in some really early episodes about some other results from looking at particles that were detected in some of the plumes coming off Io, I think it was.
Yes, I think that's right. That sounds right.
Yeah, so we have, and
geez, that was an early episode, wasn't it?
That was a long time ago. But yeah, we have looked at some of that data before, and it was looking at measurements of gravitational fields on things like Europa, seeing how that, obviously not going down and measuring it with a stick, but using its proximity to the moon to look at maybe how dense is it, how big is this underwater ocean. So there were loads of science questions that Juno was up to. And it was a very successful mission.
All right. So, Emily, we've kind of danced around this one, but I think it might be time for another Emily Brunsdon patented stat attack. So can we have a Jupiter statistical rundown here? Do you want to test me on some numbers?
Yeah, well, it's not so much a test. You might have to guesstimate some of these numbers, but I'll forgive you if you...
Mate, there's going to be no estimation in the guesstimation here. It's all going to be complete guesswork. So
I thought we should talk about wind speed, because we're talking about the fact that the outer ring of the spot is speeding up, which means the wind speed is speeding up, right?
And this is a big storm. Like we've established, it's a storm. It's like a cyclone, but it's really big. So I've got an image in my mind of take the biggest storm ever on Earth and then just make it bigger. So I'm ready.
Okay, well, let's start on Earth. Do you know what the highest wind speed that's ever been recorded on Earth?
No. Hundreds of kilometers an hour. Yeah. I'm gonna guess 200 kilometers an hour.
Whoa. That's a mere sort of breath of air.
Serious?
Yeah, seriously. The probably the most famous measurement is something called the Big Wind.
Geez, we name things well. Was that named by an astronomer or an Australian or both?
Well, actually, that's very interesting because we're going to talk about an observatory and then we're going to talk about Australians. Anyway, the Big Wind actually was recorded at Mount Washington Observatory, which is probably part of its fame, but it did hold the record for being the highest wind speed that wasn't in a tornado. We got to kind of just put tornadoes...
Yeah, tornadoes are weird anyway.
They're different, and we struggle to measure them anyway. So, excluding tornadoes, the highest wind speed was recorded at 372 kilometers per hour.
Wow, that's almost twice what I said. So, yeah.
And that was the record until 1996.
Yeah. What happened in 1996?
Wow, we had Tropical Cyclone Olivia. Mm-hmm. Do you remember that one?
Like kind of vaguely, yeah.
It hit various places in Australia, including Barrow Island.
Oh, yeah, ringing a bell. I mean, I wasn't in Australia at the time, but yeah, this is ringing a bell.
So that gust got to 408 kilometres per hour.
That's insane. The wind shouldn't get that fast. That's just not on. That's not okay.
It's huge, isn't it? It's huge. So, I mean, the estimated speed, or the speed that we're seeing now in the outer clouds, the outer ring of Jupiter's red spot. Do you want to have a go?
So if the highest speed that we've recorded in the world is, let's call it 400, round it down to the nearest 400. Jupiter's a lot bigger, but then again, I have absolutely no idea of the relative atmospheric thicknesses and blah, 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 blah. So I'm going to guess it's faster. And I'm going to guess it's faster by a factor of 2.
Ooh,
so I'm going to say 800.
Interesting. It's not that high. It's around, maybe 430, 440.
So, not far off.
Yeah.
Let's call it the same.
Pretty much.
Yeah.
And that's the measurement that's increased by 8% over the last decade.
Right. Okay. So it's yeah, I mean, that's about the same as the fastest speeds you get on Earth, which is surprising, given the size of that storm. And maybe size is irrelevant. I don't know. Atmospheric scientists, email us and tell us where I'm going wrong here. But I would have guessed that you would have got some really quite full-on serious speeds there. And instead, it's just, terrifying, but still not quite where I thought it might be.
Well, if you want to crank it up and find out some sort of slightly more exciting records.
Go on then.
Where's the highest wind speed in the solar system, would you think?
Well, where could it be? I mean, if it's not Jupiter.
It's not Jupiter.
And I'm guessing, by the way, that the Great Red Spot, or the slightly less great white-ish spot, depending on what we want to call it in the future, I'm guessing that that's probably where you're going to get the fastest wind speeds that we've seen on Jupiter. Okay, so we're leaving Jupiter behind. Saturn, I have no idea. Venus, I know, is a pretty nasty place to hang out. I'm going to guess Venus.
It's Neptune.
Neptune?
Neptune.
Who knew Neptune had evil winds? How fast does it get to Neptune?
Well, take a stab.
Okay, for this one, I'm going to say 800. Double the Earth. Yeah?
You're going to have to more than double again.
Seriously?
1,770 kilometres per hour.
On Neptune.
On Neptune.
Neptune, you little dark horse, you. Where did that come from? What's going on Neptune that gives us those kind of speeds?
Yeah, a lot of wind.
Yeah, well, clearly.
Yeah.
Wow.
It's just an interesting thing about being an ice giant. You get that, I guess there's a lot of warming. You got massive winds going through the atmosphere. It's just crazy.
Okay, I was about to ask you all sorts of questions about Neptune. That's going to take us way away from the Great Red Spot. I think maybe we need to do another episode about Neptune at some point.
Absolutely.
I don't actually even know what you mean by it's an ice giant. So let's just park that and come back to Neptune, its ice gianticality, and its wind speeds another time, okay? Sometime before episode 100, we're going to do Neptune. Right, okay, park it. Yeah.
Final one.
Yep.
We have got a record for the highest speed, I guess, modelled, probably more than measured, on an exoplanet. Mm-hmm. Do you want to ever go?
Oh, we've done shows about this before, Emily, where we've talked about exoplanets, planets around other stars, where there's been hideous wind speeds which blowing around shards of glass that are precipitating out of the atmosphere. And so I'm going to guess it's up in the thousands of kilometers an hour. Like, let's say 3.
8,700.
Like, the universe is terrifying. You got all this space and it's cold, and then you come across a planet and go, oh, what's this like? Oh, it's 8,000 kilometers an hour and it's horizontal glass rain. No, go home. I'm just going home.
So, I would strike HD 189733B off your next holiday destination.
Right. So the Great Red Spot's looking pretty good at this point as being just the wind speed of the worst storm on Earth. I'll take that and run. That's insane. Okay, so leaving Stat Attack behind, I've clearly failed in my knowledge of wind speeds in the universe. Bringing it back around to the research paper that we started with, right, which was talking about those wind speeds of, around the boundary of the Great Red Spot. And if I remember correctly, they have been getting faster.
They have,
okay.
Yes.
So why? What's going on?
Well, okay, you're asking the hard questions now.
Okay. Can I ask that one in a minute?
Yeah. Let's start with, we'll just remind everybody that what we're looking at is, say, wind speeds of maybe 400 and something kilometers per hour, increasing by, maybe 8% over a decade, just over a decade, which, if you kind of track that into future, is fairly terrifying. But anyway.
Yeah. I mean, if that continues, that's not a great trend. But, who knows? Who knows? So it's gone from let's call it 400 to let's call it 440. It's gone up by roughly that amount. Yeah.
Yeah. Why? I mean, because the storm is slightly changing, because the atmosphere of Jupiter is just slightly changing. I don't think we've got a particularly succinct, pithy answer to that.
Right. But I mean, with a system which can, over a period of time, change the size, at least in one dimension, of this storm by like a really significant amount. Like, didn't you say it had sort of halved in
100 years?
Yeah, halved in 100 years. To then change wind speeds by, let's call it 10%, is not hugely surprising. Like, there's a lot of angular momentum and energy to be shuffled around here. Yeah. And when you're changing the dimensions of this thing so significantly over the course of 100 years, then, it's all got to go somewhere.
Absolutely.
And
yeah.
So an increase in speed of one part of it or all of it of 10%, I'd buy that. Sure. That kind of makes sense.
I guess where it becomes particularly relevant is that these kind of measurements, which are not easy to make, let's be honest. You sort of think, oh, yeah, we'll look at it, we'll watch it for a while and see how fast it goes. Doesn't really work.
It's not that easy?
No, it's not that work. What you've got to do is kind of generate vectors, which are little arrows that represent both distance and time, so basically speed of a particular point. And in this case, the authors looked at tens of thousands of these vectors and tracked them over the course of 10 years. So it's a significant piece of computational work.
That's non-trivial. I'm guessing there's a lot of computers involved in this, in finding patterns and mapping things out and automating it. It's not people poring over photos going, that bit there, next photo, that bit. It's not that. No, there's a lot of computers involved. Even so, that's a lot of data to draw through.
So if you're going to spend that much effort, I guess the natural question is why? What's the point?
Yeah. I mean, sometimes we do things, Emily, just because it's fun. But I'm guessing that there's a better answer than that.
Not a lot of scientific research gets funded because it's fun.
Oh, come on. Putting the fun back in funding?
Oh.
So why were they looking at this?
So this is all to do with the fluid dynamics and understanding atmospheres, because let's face it, we've got very different atmospheres here in the inner solar system, which we can study. And like from all accounts of people that I know who study even Earth's own atmosphere, there's a lot to be kind of found out more that we don't know and understand.
It's hellishly complicated. Really, really nasty.
So it's not surprising then that when you go to a kind of a completely different system, a completely different type of atmosphere in terms of our solar system, back to a primary atmosphere, that we need data to even begin to unravel what is this atmosphere doing? How is it going to change over time? And Jupiter gives us a lot of this information in a way that some of the other planets like Saturn don't, because Saturn's just kind of a yellow ball. It's lovely to some.
Yeah, no offense or anything. But it doesn't have the same kind of obvious features at the sort of atmospheric level that allow you to do that kind of pinpoint, that bit there, where's that going? Okay, follow that computer model. It's much harder / impossible to do.
Yeah, so Jupiter's a great testing ground. So if we want to understand where is the energy coming from, where do these storms come from, how long do they last, what effects do they have on their host planet? And then that instantly tells you that the next question would be, well, how does the stuff that we learn about our solar system apply to planets in other systems? How do we find out if their atmospheres are lovely and nice like Earth's, or horrible and nasty like Jupiter's?
Absolute hellscape.
Or even worse like Neptune's.
Yeah, because it's all model based, right? Yeah. And so models depend on some really good guesswork, some really good theory, and a whole lot of data. And then you just iterate that, run your model. Does it match? Put more data in, make more educated guesses, get a few more equations, put more data in, cycle. And so observing the hell out of Jupiter helps those models.
Absolutely. Yeah. So it's cool. I mean, I love it how that, okay, we don't always have to go to exoplanet science. I know it's sexy and exciting and...
But why not? Do it anyway.
In my opinion, maybe slightly overfunded. But... only compared to other areas of stellar physics. But no, I mean, honestly, we don't always have to take that leap, but I think it's interesting too in this case.
Right. Well, we have, I feel like we finally, after 80-something episodes of this podcast, got to something which is a pretty obvious thing to do a podcast about in an astronomy podcast, which is the great red spot of Jupiter. We finally got there. And not only that, Emily, we've actually identified another thing that we really need to talk about, which is Neptune, which is just up the road from Jupiter. It's actually quite a long way out, isn't it?
Yeah, it's quite a way.
Yeah. The distance scales are nuts, aren't they?
You got to walk to Heslington East to find our Neptune here at York.
Yeah. That's right. It's a really long way away. All right. Well, look, we'll do that in a future episode. But listen, if people want to get in touch with us and correct any of the, I don't know, idiot mistakes that I've made during the course of these various podcast episodes, or suggest an idea for a future podcast, like, I don't know, Neptune and its iciness, then are there ways that they could do that, Emily? How could people get in touch?
Oh, we have all of the ways. We have our own website, which is syzygy.fm. That's SYZYGY.
Well done. Yes.
I can do that now. I've been practicing.
Very good. Episode 84. You're really, really good at that.
Yeah.
Yeah, you can find all of our past episodes, all of the info, all of the links, all of the pretty pictures, everything, as well as a contact form where you can send us your thoughts and ideas and applause and congratulations and love. So you can do that through the website. How else?
You can do it in a fewer characters in your favourite form of Twitter.
Right, yeah.
So we are SyzygyPod, at SyzygyPod, with the same spelling of Syzygy, but with a POD on the end.
POD on the end, yes, indeed. We're also on Instagram, I think.
Yeah.
SyzygyPod.
I think that's a thing.
Yeah, pretty sure.
I'm told it's a thing.
And of course, we're on the Facebook as well. So if you go and just search for us at Syzygy Podcast, then you'll find us there too. If you want to support the show, tell everyone you know. That's the best thing. Find the person in your life that you think would get a kick out of talking all things universe and tell them that they should go and listen. You should give us a rating and give us a review on your podcast client of choice. And if you want to become a financial member of the show, then you can go to patreon.com/syzygypod, where you can sign up to pitch in a buck, a pound a month or more to help us keep the electrons flowing and to help us do the things we love to do when the world's opened back up again, like live shows and festivals and stuff like that. So those are all the different ways that you can support the show. Listen, we should get out of here. Emily, it's been fantastic as ever. I will catch up with you in a week or so's time.
Yep. See you later.
All right. See everybody. Bye-bye.
You know how, like, in the 90s and so on, there was all these, like, films about tornado chasers and how, like, mad they were.
Yeah. And they do crazy things like, there's a big tornado. It's the biggest tornado we've ever seen. Quick, drive our truck towards it. Go, go, go. And then we'll throw something in.
It was just mad, isn't it? So do you think that, like, people who study Jupiter are kind of, in a way, like storm chasers?
Could be. That's a frightening thought.
Because, you know, Hubble just sits there and puts out storm reports.
Seriously?
It does. I've never sort of sat and thought about it. Hubble, the space telescope, it's pumping out its storm reports.
Do you know what? If there are any Hollywood producers out there, I think I've got an idea for a screenplay.